In this video, we're going to continue our discussion of um, the frequency response of a system, or of a response of a system to a sinusoidal or harmonic input, and these plots that we drew in the previous video. And these plots, they have a special name. They're called bode plots. Mm. Um, and so what they show us, again, is how as the frequency increases on this horizontal axis here, it'll tell us the magnitude of the response and the phase offset of the response. And we can classify various um, various types of systems based on what these plots look like. So for example, this plot, we had a magnitude that was high or a high magnitude at low frequencies, and as um, the magnitude increases, or as the frequency increases, the magnitude drops off. And so we call this a low pass filter. That means that if we give an input of with a low frequency, that low frequency is allowed to pass through the filter at a magnitude that's more or less unchanged. But if we start to increase the uh, frequency to, uh, if we start to increase the frequency, then that magnitude is going to decrease, and we're not going to get that high frequency information in the output of this system. Um, so a low pass filter, the magnitude kind of looks like this, where you've got high magnitude at low frequencies, and then as the frequencies increase, the magnitude drops off. We also have a high pass filter, which does the opposite, where at low frequencies, not a lot of information is going through, but at higher frequencies, you get the same information, or you get the same magnitude out of the response. You can combine these to create a band pass filter, where both low and high frequencies are filtered, but the middle range frequencies are allowed to pass through the filter. Um, and then the opposite of that would be a notch pass filter, where you have a high frequency and then or a low frequency and a high magnitude, and then it drops down, and then you want higher frequencies to pass through as well. Um, so certain uses for each of these. You might, for a low pass filter, you might have some sort of noise suppression. So if your data is noisy, um, you can, if that noise has a high frequency, you can get rid of it with a low pass filter. Um, you might be able to use a high pass filter for if you're interested in something that happens at a if you're interested, um, maybe there's some low frequency background noise happening. So the example that I use in mechatronics is if you're interested in measuring, um, if you have a light sensor that's going to be out both at daytime and at nighttime, you have a really low frequency noise in that system that comes from the sun going up and going down, and the light, that ambient light, is changing at a frequency of 1 cycle per day. But maybe you're interested in seeing a blinking light that's across the field or something. You would use a high pass filter to get rid of the changes that come about from the sun in that situation. Um, so if you're interested in high frequency noise signals. And you can imagine systems, I'll let you try and think of systems where a band pass or a notch pass filter, where if you're trying to measure something that is at higher, that's only at intermediate frequencies, or if you're trying to create something, um, then then you might be able to use a band pass or a notch pass filter. And so with these systems, if you're using, so I'll draw another um, low pass filter here. We characterize these systems, these filters, with something called a cutoff frequency. And the cutoff frequency is going to be right about there, and it's the frequency at which the magnitude ratio B over A equals 0.707. And that's where your omega sub c, or your cutoff frequency, is going to be. So if you want if you want to be able to design a filter that cuts off or amplifies frequencies higher or lower than a certain frequency, then that frequency would help you determine your cutoff frequency, where everything below that you're not as interested in, and everything above that you want to make sure to keep. These same plots, so we've been talking about magnitude plots, but we also have the phase plots, which often look like this. And at that cutoff frequency is where you're going to get this midpoint, where often with these systems you'll have 0 up here and negative 90 degrees or negative 180 degrees, depending on your system, down there. And this is what's called a lag compensator. Let me check that. So if your phase is less, or it's called a lag compensator. So if that phase offset is less than 0, that means that your response happens after your original signal. So if your original signal is a sine wave that looks like this, if your phase offset is negative, then that means that it does the same thing after here. How can I draw that? It does the same thing as your input, but a few seconds or some time period later. A lead compensator allows you to help predict what's going to happen, and that makes the same thing was going to happen before your input does it. And that just depends on the phase. So a lag compensator, if your phase is less than 0, I'll just write phase as a phi. Lead if phase is greater than 0. We'll go ahead and end that video right there.